All right, so get this. We're going deep today into string theory.
Oh, wow.
Yeah, it's a theory that's trying to answer some of the biggest questions in physics, and I'll be honest, it's mind-bending,
Oh.
even for the physicists who work with it every day. So
Yeah,
if it sounds a little crazy, that's okay.
absolutely.
We're all kind of in the same boat here. The basic idea is that everything in the universe, I'm talking everything from the tiniest particles to those massive black holes,
Right.
it's all made up of these incredibly small vibrating strings.
It's a pretty wild concept.
It really is. Like, imagine a cosmic symphony, but instead of making sound, these strings, they're actually creating the fabric of reality.
Yeah, it's not just about understanding like individual particles or forces, right?
Yeah.
It's about this whole idea of finding a unified framework.
Right. A theory of everything.
Yeah, exactly, like a theory of everything.
Yeah.
That explains the entire universe at its most fundamental level.
And to help us kind of navigate all this, we're turning to Leonard Susskind.
Oh, wow, a pioneer.
Yeah, he's not just an expert, he's one of the founders of string theory.
Right.
And we're lucky enough to have access to his latest thinking on where the field stands.
That's awesome.
The successes, the struggles, the whole 9 yards. But we're not going to just skim the surface here.
Yeah.
We're going deep,
Okay, let's do it.
exploring the criticisms, the potential, what Susskind thinks needs to happen next.
I mean, it's super elegant from a mathematical standpoint,
Yeah?
but there are definitely challenges when it comes to like actually aligning the theory with what we see in the universe.
Exactly. So to set the stage here, I think most of us are kind of familiar with the basic idea that the universe is made up of these tiny particles.
Right, like electrons and quarks.
Yeah, things like that. But string theory takes it a step further, right?
Mm.
It suggests that these particles aren't just like points, but they're actually the result of these super tiny vibrating strings.
It's like, you know how you can play different notes on a single guitar string?
Right.
String theory is saying that different vibrations create different particles.
Yeah, that's a really cool analogy, but
Yeah, it is a simplification, though.
oh, for sure, for sure.
What makes it so exciting for physicists, though, is the potential to unify quantum mechanics,
Right.
which governs the tiny world and general relativity, which explains gravity on this grand cosmic scale.
Okay, and these two frameworks, they've kind of resisted unification for a really long time.
For decades.
So string theory is offering a way to bridge that gap.
Yeah, exactly. Like, imagine you're trying to fit together two puzzle pieces that they don't seem to fit.
Right, they're totally incompatible.
That's kind of what we're dealing with here.
Okay, and then string theory even proposes that there are these extra spatial dimensions beyond the three that we experience.
Like up, down, left, right.
Exactly. I know it sounds crazy.
It does.
But these extra dimensions, they might be curled up at these scales we can't even imagine.
And that could be the key to making the math work.
So we're talking about theoretical physics here.
Right. And the math is undeniably elegant,
Yeah.
but it needs to connect with observable reality,
Right.
right? And this is where we start to see some of the criticisms.
Okay, so this is where the cracks start to show in this seemingly perfect theory.
Yeah, Susskind points out this fundamental discrepancy.
Okay.
String theory relies on anti-de Sitter space.
Okay.
But our universe, it's more like de Sitter space.
I mean, it sounds pretty technical.
It is, but it has big implications.
So it's like having a clock
Okay.
that's beautifully designed, perfectly functioning, but it just tells the wrong time.
Exactly.
Okay, so are we talking about just needing a minor adjustment to the theory?
Yeah, or does it go deeper?
Or is there something more fundamental that's off?
Right, and it gets even trickier when you bring in supersymmetry.
Okay, and just to remind everyone, supersymmetry is the idea that every particle has a partner particle
A superpartner.
that we haven't found yet.
Right, and so far,
Again, no luck.
nothing.
And this is where Susskind is really pushing for a change.
He's not saying we give up on string theory.
Right.
He's saying, hey, it's your turn, like to the younger physicists. He's 84, and he's basically saying, don't be afraid to challenge the foundations. Reimagine the possibilities.
So less about throwing out the theory, more about rethinking the fundamental assumptions. And that's what makes theoretical physics so exciting, right?
Absolutely.
You get to question, push the boundaries.
Yeah, it feels like he's passing the torch to a new generation
Right.
to solve this cosmic puzzle.
What do you think it would take for a younger physicist to make some real progress?
It's a good question, and it's the kind of question that Susskind wants us to be asking.
Right.
He's not giving us a roadmap,
Right.
but he is telling us to think bigger, think outside the box.
Think beyond the conventional boundaries of string theory.
Yeah, maybe a radical shift in perspective is what we need.
A paradigm shift. Now, that's a challenge.
Yeah, It's fascinating to think what a paradigm shift would even look like.
Yeah.
We're talking about challenging everything we think we know about like space and time and even reality itself.
I know, and that's what I find so exciting about all this. It's not just about particles and equations, it's about like the very essence of how we understand the universe.
Right.
And when you look back at the history of science, I mean, do these big breakthroughs, do they come from, like building on what we already know, or do they come from these radical shifts?
That is the question, isn't it?
Yeah.
I think if you look back at the biggest changes in science, you see both. You know, sometimes it's a bunch of small steps that lead to a breakthrough.
Right.
And then other times it's a totally revolutionary idea that just changes everything.
Right, like going from Newtonian physics to Einstein's theory of relativity.
Exactly. That was a huge shift. Nobody saw that coming.
So with string theory, are we trying to figure out if we need a course correction or a whole new map?
Yeah. And remember how we talked about how there's tension between the math and what we actually see?
Right.
Some people say that string theorists are kind of moving the goalposts.
What do you mean by that?
Well, instead of questioning a theory itself, they just change how they interpret it or add new things to make it fit the data.
So instead of finding a peg that actually fits, they're just making the hole bigger.
It's a little more complicated than that, but yeah, you get the idea.
Yeah, but how much can you change a theory before it just doesn't explain anything anymore?
Right, and that's a huge debate in physics.
I mean, if you're constantly adjusting a theory to fit new observations, is it really reflecting reality?
And that's why Suskind's call for fresh perspectives is so important.
Okay.
Maybe we're too attached to certain ideas in string theory. Maybe we need to step back.
Yeah.
What if there's a completely different way of looking at it that we haven't even thought of?
A path less traveled. And this makes me think about those alternative theories like loop quantum gravity.
Right.
How does that approach this problem of unifying quantum mechanics and general relativity?
It's completely different. So instead of strings loop, quantum gravity says that space-time itself is made up of these tiny loops.
So it's like the fabric of reality is a woven tapestry with each thread being a loop of space-time.
That's a good way to think about it.
And how does that address the issues that string theory has, like needing those extra dimensions?
One big difference is that loop quantum gravity doesn't need those extra dimensions.
Okay.
It tries to quantize gravity just with the 4 dimensions we already know about.
So it's more grounded.
Yeah, and that's why some people are excited about it.
But is it like a competition string theory versus loop quantum gravity?
No, I wouldn't say it's a battle.
Okay.
It's more like different explorers charting the same territory.
I like that.
They both want to find a theory that explains how everything works.
And maybe the answer comes from combining these different approaches, or maybe something totally new.
Or something we haven't even imagined yet.
Exactly. And even if string theory doesn't turn out to be the be-all and end-all, it's already changed how we think about physics.
It's opened up all these new ways of exploring the universe.
It really has pushed the limits of what we know. But before we get too philosophical,
Right.
there's another cool aspect of string theory that we need to talk about.
Okay.
Black holes.
Oh, yeah, those are fascinating.
Yeah.
Gravity gone wild.
This is where string theory gets really sci-fi.
Yeah.
We're about to enter a whole new dimension, literally.
I'm ready.
So black holes, these objects where gravity is just so strong, nothing, not even light can escape.
Yeah, they're like the ultimate cosmic dead end.
And at the center of a black hole,
Yeah.
we have a singularity,
Right, according to Einstein's theory of general relativity, at least.
which is a point of infinite density.
Yeah, where all matter is squeezed into this unbelievably tiny space.
Okay, now my brain is starting to hurt a little bit. Infinite density.
Yeah, it's hard to even imagine.
It really is. But this is where string theory offers a new perspective.
A different way of looking at it.
Instead of a singularity, string theory suggests that at the heart of a black hole,
Uh-huh.
there might be a fuzzy ball of strings.
Fuzzy ball of
Yeah.
strings.
It sounds a lot more cuddly than a singularity.
It does. But keep in mind, we're talking about strings at energy levels that are just mind-blowing.
Yeah, beyond anything we can even observe.
And those extra dimensions that string theory talks about,
Right.
they can become really important at those energies.
Okay.
Instead of being all curled up, they could unfurl and smooth out the singularity.
So instead of everything collapsing into a single point,
Right.
it gets spread out across these extra dimensions.
Kind of like if you imagine a black hole warping space-time, but instead of a bottomless pit,
Right.
you have this fuzzy ball of strings.
Okay, I think I'm starting to get it. So what does that mean for all the information that falls into a black hole?
That's a great question because classical physics says that anything that falls in is gone forever.
Yeah, like it's just completely destroyed.
But string theory suggests something different.
Okay.
It says that information isn't destroyed, It gets encoded in the vibrations of those strings.
So it's like a cosmic hard drive storing everything that's ever fallen in.
It's a really cool idea, and it shows how string theory is changing how we think about black holes,
It's making us rethink some of our most basic assumptions.
forcing us to be more creative.
This whole conversation about string theory, its challenges, its possibilities, it's amazing how we can use math and theory to explore these big mysteries.
It really shows how curious humans are,
We want to understand the universe.
our place in it.
And even if string theory doesn't give us all the answers,
Right.
it's definitely helped us learn more about the cosmos.
Opened up new ways of thinking.
We've gone from tiny strings to massive black holes today.
It's been quite a journey.
And I feel like we've only just scratched the surface.
There's always more to learn.
Exactly. So to everyone listening out there,
Yeah.
keep asking questions.
Keep exploring.
And never lose that sense of wonder. You never know what incredible discoveries are waiting out there. This has been The Deep Dive, signing off.